And this is the 90-minute session before we have a long break, and then the final plenary or keynote session. Your next speaker, I'm not sure you need any introduction, Drew. So Drew Troyer is clearly the reliability engineer's reliability engineer. There's nothing I know about reliability engineer that Drew hasn't forgotten or has probably taught me in the first place. So Drew is he's a certified reliability engineer. CEM is the American for energy management. Oh, that was the energy management one. I mean, the list is endless of the stuff that Drew's certified in, and then he's also written the book on it. He's a globally recognized authority on the topics of physical asset management, energy management, and sustainability. He's got more than 30 years experience and brings a wealth of knowledge to the table. I personally worked a lot with Drew over the last, I'm not going to give my 20 years, longer. Massive respect for Drew and his deep knowledge of all things reliability. So Drew's going to share with us his thoughts over the next 90 minutes on the asset management's role, manager's role in energy management and sustainability. Drew is really looking forward to quite a lot of interaction, so feel free to, if you don't agree with Drew, and there have been times, I think once or twice, where we haven't agreed. So by all means, he's looking forward to some vibrant debate as well. So without further ado,
thank you, Mike. So this is actually a preview of a new class that we're rolling out in asset schools, which is around energy, sustainability, and decarbonization. So as Mike said, I've been doing this for over 30 years. I started out actually in the power generation industry in the 80s, and was one of the guys who brought condition monitoring into industry. So as microprocessors became available, we transitioned from our old school approaches to maintenance to some more modern approaches to maintenance. I'm not really sure that they work better than the old school ones did, but the transition has occurred just the same. Some years ago, it became apparent to me that decarbonization was going to be something of critical interest to most organizations. And so I decided to get a master's degree in environmental management sustainability. And I had a professor, world-renowned sustainability guy, who was the professor. His name is Dan Schrag, and he was teaching a class called Confronting Climate Change. It was a very, very deep technical class, but the latter part of the class was turning the tables. Rather than teaching us about climate change, he challenged everyone to focus on how are you individually going to contribute to confronting climate change, because there is no silver bullet. It's a very complicated issue. I know this morning we talked in somewhat esoteric terms about the challenges of industry, and I really enjoyed Saul, our keynote speaker's address, but that's a highly simplistic solution. Just electrify everything. Just turn the switch and just electrify everything. It's very challenging. If it was easy, it would be solved, right? It's not easy. So I decided that based upon my history, the best way in which I could confront climate change is to focus on energy efficiency of the operations that we work on. So, and I do agree with what Saul said this morning. We can't just focus on energy efficiency and solve our problem. But it ain't gonna hurt, right? It certainly is not going to hurt. And so what I'd like to do is take this morning's somewhat esoteric discussion and bring it down into something that affects your lives and really focuses on some things that you and I can do to address climate change. So I'm actually, just now, I've decided to accept a post. In addition to being a partner with Bootleg Advisors, I'm now the global head of asset management for Anglo American, globally for all of our operations. So I'm having to actually put this to work in addition to doing the other things related to asset management, shutdown management, condition monitoring, master data and EAM systems, so on and so forth. But it is a big opportunity for us, and I hope that you see it that way. So the focus for today's session is, what is your job? What is your job in terms of helping your company decarbonize? And as a reliability engineer, as a maintenance manager, as a maintenance engineer, as an asset manager, as a planner, whatever the case may be, chances are pretty good you are not going to be developing the world-changing energy technologies. You, like me, are responsible for running equipment. But there are some things that we can do to help achieve those goals. The other thing that we need to think about is, what are these transitions going to do to us, and are we prepared for them? Renewable energy sources, which are bound to be a part of everything that you're looking at. So I mentioned this morning, at Anglo American, we're experimenting with hydrogen. It's a very challenging energy carrier. We are experimenting with pyrolyzing tires, our used tires, to turn them into fuel. So we're experimenting with all kinds of decarbonization strategies, which mean that running the plant or running the mine is even more complicated than it used to be. So we need to prepare for that. And I'm going to get into some examples of energy storage. So we'll talk about the common, I'm going to say, renewable energies that you might run into as a part of your organization. I'm not going to go into everything. I'm going to talk about the big ones. And then I want to talk a little bit about storage. One of the challenges that we have with renewable energy is it's not what we call in the energy business dispatchable. So if you don't know that term, dispatchable, what it means is when you turn on a light switch, what do you expect to happen? Well, you expect the light to come on, right? You want that energy dispatched right now. Well, if you have intermittency in your supply, you won't have dispatchable energy unless the timing just happens to be lucky. Unless, of course, you put in place storage mechanisms. I'm not going to go into comprehensive examples of pumping stations and this, that, and the other. That's really more for the two-day course. But I do want to provide a worked example of some of the challenges that we face in real life in our various industries. So how many people like me are in the mining industry? Yeah, so that's what happens when you go to Western Australia. You get a lot of miners. Seems to be the same thing in Johannesburg, right? So you guys face a lot of the same challenges that I face. So I think my worked example will speak to you. And I'm going to talk about what I call the dirty dozen challenges we face in terms of dealing with new sustainable energy. And then I want to get into the core of what I really want to discuss, what we can do. I think, based upon the U.S. Department of Energy, in the mining industries, and really industry across the board, just by implementing existing best practices, we can reduce our energy consumption by 20%. That's what I really want to talk about. What can you do to reduce the amount of energy that you consume? Because if you reduce the amount of energy you consume, you by definition reduce the carbon impact on the climate. So, and I'm going to go through, and bluff just means bottom line up front. I'm going to go through some of the key things that you need to be focusing on. And then I've got, if I have time, I've got more slides than I've got time to present. We'll go into sort of a deep dive on all of those as it relates to some of the common systems that we're dealing with. So electric motors and the systems that they drive, pumping systems, compressed air systems, so on and so forth, engines, some things that you can do to take action actually in the fairly short term to not only improve your energy consumption, but actually improve the reliability of your equipment. We'll talk about that in a little bit more detail. So I've identified what I consider to be the 6 primary sustainable development goals. So these are you've seen the UN Sustainable Development Goals. There's 17 of them. And I think that sustainable manufacturing or sustainable asset management, which is what we're talking about predominantly in this master class, deals with all of them to a lesser or greater extent. But these are the 6 that I think really have the greatest bearing in terms of what we're discussing today. So as asset managers, as reliability engineers, whatever the case may be, effectively, energy is our job. We have the responsibility for ensuring that energy is efficiently and effectively converted from one form to another. Then we want to ensure that that energy is efficiently and effectively transferred along its intended pathway, and then we want to make sure that that energy is efficiently and effectively utilized to do whatever it is that we're trying to do. Whether we are drilling, whether we're shoveling, I'm using mining terms here, whether we're hauling, whether we're crushing, whatever in the process. That ultimately is our goal. So, what do we mean by efficient conversion? Well, a lot of the energy that we use in the mining industry, in particular for our fleets, is what we call chemical energy. So diesel energy is chemical energy. We need to convert that by combustion into mechanical energy. That mechanical energy either drives an alternator to drive wheel motors, or if we have equipment that's mechanically linked, it drives shafts and differentials, so on and so forth. So we need to make sure that the conversion process is as efficient as possible. So whether you have a furnace that burns natural gas, or you have an engine that burns diesel, any chemical form of energy, we want to make sure that we are combusting or converting that energy as efficiently as possible. So in my world, I somehow or another wound up in the mining industry. I'm not exactly sure how. That was kind of an accident, I think. I was here working with Chevron and somehow or another wound up in the mining industry. I think it's what PERTH does to you. So in the power generation industry, we have engineers that are specifically focused on combustion, tuning combustion systems to ensure that they have just the right performance. Not too lean, not too rich. Combustion engineering is its own discipline. So we want to make sure that we have efficient conversion. We also want to make sure that we have efficient transfer. So whether we have mechanical linkages or we have electrical circuits, we have steam systems, we have pressurized air systems or other pressurized gas systems, we want to make sure that that energy, once it's converted to a desirable form, is transferred as effectively and efficiently as possible. And then we want to make sure that it's used. Whether it's an electric motor, a diesel engine, pumps and compressors, whatever the case may be, we want to ensure that it's used effectively. Now, if energy is not converted efficiently, it's not transferred efficiently, and it's not utilized efficiently, it manifests itself in the form of waste. Probably the biggest is heat losses. Friction's a big driver. You know, our combustion engines, even if at their best, they're 33% efficient. Where does most of the energy go in an engine? Out the tailpipe as heat. Electrical resistance, all right? If we have, for instance, undersized electrical cables, or we have cables where we don't have good connections between cables and connectors to terminals all along the circuit, if that's not properly designed and properly maintained, we have I square R losses, resistance losses along that circuit. Air resistance, conversion losses, so on and so forth. One of the things that's a real pet peeve for me, in fact, I'm not sure who I was talking to about it. It's a new plant that went in. I think I was talking to the Talisman guys, some of the Talisman guys. It's a new plant that went in, and they're pumping slurry. And the design engineers put a lot of hard 90-degree turns in the piping. What's the problem with that? Frictional losses. In that particular case, when you're pumping a slurry, it's also going to wear out, you know, those 90-degree turns. So why do we use so many 90-degree turns in our piping systems? It's convenient, it's cheap on the front end, so it's easy for somebody to do that. And what's interesting, the design engineers and the EPC firms that make that happen, they actually get a bonus for doing that because they come in, you know, cheap and on time. But your life cycle impacts, changing out those elbows, dealing with the energy loss, those are quite impactful. The other thing that we need to focus on is effective recovery. So in the power generation industry, we kind of transitioned to utilizing a lot of what are called combined cycle generation systems, trying to move away from coal. The reason we wanted to move from coal to natural gas in the power generation industry is multi-part. One, coal is a gigantic pain in the backside. Gas is relatively clean, but very importantly, per kilowatt hour, natural gas produces approximately half of the carbon dioxide as does coal. The reason is that coal has a very high ratio of carbon to hydrogen, whereas natural gas has a very high ratio of hydrogen to carbon. So natural gas is predominantly methane, CH4. So there's 4 hydrogen atoms for every carbon atom, whereas with coal it tends to be 1-to-1, or in some instances, depending upon the type of coal, you've got more carbon than hydrogen. Well, to form carbon dioxide, you need those carbon atoms. So that's one of the reasons. Well, when you use natural gas in a gas turbine, you lose a lot of heat. So what we have is what's called combined cycles. We grab that exhaust heat and use that to fire a boiler that it in turn drives a steam turbine. So we recover some of that energy. Now our job, I've put us right at the top here, is maintenance. What role does maintenance have to play in this? Any role at all? Quite a bit. A lot of the practices that I'm going to talk about that are within your control, the things that you can do starting today, have to do with managing different aspects of mechanical and electrical maintenance. So that's what I really want to focus on today, the things that you can do. Okay, so there's lots of different forms of renewable energy, and I'm not doing an exhaustive coverage here. I do want to talk about wind and solar. They're going to play a heavy role going forward in our renewable energy. The 2 big ones that I've omitted are hydropower and geothermal. And I've omitted those because they're very geographically specific. All right, so for instance, in the Pacific Northwest of the US, which would be the Pacific Southwest of Canada, there's tons and tons of hydropower, tons of hydropower. We've got some hydropower here in Australia. Snowy River is a fairly large hydropower complex, but I don't think we have a lot of hydropower in Western Australia. So it's very geographically specific. Likewise, geothermal energy. Iceland is great because all of their energy is geothermal. Downside is you've got volcanic activity that kind of goes along with it. So I've kind of omitted those, but they're in the mix. But wind and solar really do have a big play almost everywhere. So one thing about Western Australia is the wind always seems to be blowing and the sun always seems to be shining. So there's a tremendous amount of energy that can be harvested. I would say the biggest problems that we have with this abundant energy source is its intermittency. If the wind's not blowing and the sun's not shining, then we don't have access to that energy. So we have to deal with the intermittency of these energy sources with some kind of storage. So we can store energy with batteries. We can store energy using what are called pumping stations. Are you familiar with those? So this is where you have water that you pump to an elevated position when the power is plentiful and cheap, and then when it's not available, you utilize that as hydropower to drive a turbine so that you can deal with the intermittency associated with solar and wind. Now, what you need there is ample amounts of water, right? Because if you want any significant amount of energy storage, you need to have a significant amount of water. And water is a scarce resource in many locations. The other thing is you need an adequate vertical differential. You need a high place that you can pump the water. And it can be quite a little infrastructure build out to make that happen. In all instances, these technologies do have some environmental impacts. Wind takes up a lot of land space. It's really kind of harmful to birds and bats. And the problem that I have experienced kind of literally living in the environmental world, because my wife is a wildlife biologist, she retired from the U.S. Fish and Wildlife Service, is when I start talking about these forms of energy, she starts going into birds and bats, right? So these pesky environmental people, you can't seem to please them, right? They want no carbon dioxide, but they want no impacts on the birds and the bats. So the other thing is these are unsightly. Not everybody likes to look at wind turbines. The vertical turbines are a little less unsightly, but they're a little less efficient. And because of turbulence coming off of the horizontal blades in a conventional wind turbine, they can't be spaced too close together, because what happens is when you throw off turbulence from one turbine, it interferes with another turbine. So if those things are too close together, the efficiency of the whole wind turbine system kind of falls off. Now, where I live, which is in the southwest of Oklahoma, the United States, we have these massive wind farms. Massive wind farms. They take up a lot of space, which brings up another issue. Generally speaking, the places where wind farms make sense and where you can reasonably place those wind farms isn't exactly where people live. If you go to the panhandle of Texas, there's lots of space, but people don't live there. So if we're generating electricity where people don't live, what do we have to do? We have to transmit it. Further infrastructure impacts with transmission lines. and further impacts. I was just having a conversation with my spouse, and there is a wind farm that's planned to go in an area of Oklahoma, state of Oklahoma. And the reason it's going in this area is because that part of Oklahoma is becoming like a hotbed for data centers. And data centers are energy hogs. So they're putting in all of this wind energy. They're going to put storage in adjacent to it, but it happens to be in what's called karst, limestone. And specific bats live in that area. And she's very concerned about the impact that's going to have on bats. And she said, why don't they just put the wind farms elsewhere? I said, well, we can do that, but to put the wind farms elsewhere where there are very low environmental impacts, we have further impacts associated with putting in the transmission system. So it's difficult. You know, we've got, on the environmental front, you have your, what I would call your energy and CO2-oriented environmental people like me, and then you have people like Anita, the bugs and bunnies kinds of environmental people. And they don't always see eye to eye. So we're trying to make, you know, everybody happy. It's a challenge. What about with solar? What are the problems with solar in terms of impacts? Pardon? A lot of land use. And the way solar works, generally speaking, it becomes an uninhabitable ecosystem for anything that lives in that area. Maybe some insects thrive on it, so on and so forth. But your keystone species, they're negatively impacted. The other thing is, and there's some questions about this, people don't agree on it. Some experts suggest that cattle and farming work, and other animal raising activities works fine with wind turbines. Others suggest that it disturbs their eating patterns, they don't grow as fast. I don't know, it's not my deal, all right? But I do know with solar farms, you can't farm it, you can't graze it, so on and so forth. So, and once again, it's a particular, what's that? They get underneath it? If it's elevated sufficiently. Yeah. Well, I can see where they would like the shade. In fact, I've seen pictures of even wind turbines. They'll cast a shadow, and you'll see the sheeps, yeah, all huddled into the, so, yeah, yeah. I think it's great for the farmers. Yeah. 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 So we're going to be moving in that direction. But there are people that oppose these wind farms and these solar farms. So I agree. It's like there could be negative aspects, positive aspects. It's just got to be sorted out. Yeah. Yeah. So where I am seeing wind generation going in urban areas, they're using the vertical turbines. One thing about urban areas, in particular in cities with tall buildings, those buildings create a Venturi effect, and the vertical turbines work quite well in those type of environments, and they're much less problematic or disturbing. But for your conventional wind farms, yeah, I think it would not be pleasant probably living really close to one. So yeah, totally get that. Another one is hydrogen, of course, and we discussed hydrogen a bit. I've been putting a lot of time into hydrogen. I don't know if you read about it in the news or anything like that, But at Anglo American, we have been experimenting with a hydrogen truck. And as was discussed in the keynote this morning, hydrogen has some real challenges. It has very poor volumetric energy density, high gravimetric energy density. So actually from a gravimetric energy density perspective, hydrogen is about 3 times denser than, say, diesel, a little bit more than 3 times per kilogram. But man, it takes a lot of volume to equal a kilogram. So even in a liquid form at minus 253 point something degrees C, you still have about 4 to 5 times more storage requirement to equal a kilogram than for diesel fuel. So it has very poor volumetric efficiency. So storage becomes a real issue. The other issue with hydrogen is extremely reactive. Saul said today, he talked about hydrogen embrittlement. I don't know if you're familiar with that, but hydrogen embrittlement occurs when hydrogen gets temporarily disturbed and it transitions from H2 to what's called H+, or nascent hydrogen. Hydrogen in its atomic form is not stable in our atmosphere. And so what it does is it reacts with metals and forms a metal hydride and causes that material to become very brittle. Another thing that happens is nascent or atomic hydrogen can't be contained in a conventional pressure vessel. So it will actually pass intergranularly through the metal. And unfortunately, it will run into another hydrogen atom. So hydrogen does not like to be in an atomic form. It wants to become molecular hydrogen and then something else like water. So it will convene with another hydrogen atom and form molecular hydrogen subsurface, and then that leads to what's called hydrogen-induced blistering. I don't know if you've ever seen instances where welding, when somebody's done a weld on, a butt weld or fillet weld, whatever it is, and adjacent to the weld, you'll see bubbling of the material. This is particularly the case with stainless steel. Very often that's hydrogen-induced blistering. Hydrogen is also very explosive. So, if you've got it contained in a pressure vessel at H35, H70, or liquid hydrogen, H35 is stored at 350 bar, H70 is 700 bar, and then the liquid, of course, is cryogenic, minus 255. If it escapes and comes into contact with any ignition source, you have a major issue on your hand. I personally would not want to be driving a hydrogen vehicle because it's just such an... Now, there are people that will counter that say that it enters the atmosphere and diffuses so rapidly that the risk is low, but I'm not sure I'd want to take that. I'm not sure I'd want to take that chance. So hydrogen is a problem. I actually think that we should be focusing a little bit more on biofuel. The reason is, sure, nuclear fusion may be the direction we wind up, but it's unproven at this point. The first positive experiment occurred at the Berkeley laboratory in California just last year. I think it was November, the first time ever that they produced positive energy with nuclear fusion. Of course, that's how the sun works. So we're trying to replicate how the sun works, but we're probably 20, 30, 40, 50 years away from that happening. One of the reasons that I like biofuel is that it will work within the existing infrastructure. I can fill one of my haul trucks up with biofuel and it will run just like it runs with a fossil fuel. And in fact, if you make syn fuel and you make it right, you can actually control the molecular composition of that biofuel. So you can control the cetane number. So if you have a higher cetane number, you get higher energy efficiency. So the couple of different ways that we can do that. One of the challenges with biofuel is a lot of the biofuel today utilizes food source. All right, so rather than eating our food, we're turning our food into fuel. So that's certainly the case with ethanol. I'm not a big fan of ethanol because it has lower power density, but we can take all kinds of different municipal waste, for instance, and pyrolyze that waste. So pyrolysis is a process where you basically burn material, high temperature, but in an oxygen-free environment, and you produce syngas as a byproduct. And then using something called the Fischer-Tropsch method, that syngas can be polymerized into different fuels. The Fischer-Tropsch method is brute chemistry. It's been going on for eons. In fact, I work out of South Africa, and probably the company that knows more about Fischer-Tropsch than any other company is Sasol. And Sasol utilized the Fischer-Tropsch method during apartheid because South Africa couldn't get crude oil to make fuel. So they converted coal using this brute chemistry process into fuel. Well, you can do the same thing with various forms of biomass. My favorite form of biomass to convert into fuel is probably algae. The jury's still out, but algae is not really competing with a food source. You could create algae farms. What they like is they like nutrients. So you could take, for instance, sewage nutrients. They like carbon dioxide, so you could put it next to, say, a power plant, capture the carbon dioxide from the flue gas, and feed algae farms. Now, the other thing algae needs is a lot of water. But researchers are working hard on algae that is, I'm going to say, fuel grade. Not all algae are created equal, but it's algae species that make good fuel through the pyrolysis process, but they grow in salt water. So we don't have a problem with abundance of salt water. We've got plenty of that. It's fresh water that gets to be the challenge. One of the great things, though, is when you feed the algae the sewage, they actually clean that up. They use the nutrients, so it reduces your burden on the waste management side. So those are kind of the main ones that we're looking at. Biofuel, to me, is ideal in the short term. I don't know that it's the best long-term solution. I do think in the long term that we want to move toward a greater degree of electrification, but the infrastructure process, the requirements for converting us to an all-electric energy system, it's a very expensive and long-term proposition. Somebody had asked this morning about nuclear, uranium. If we were to convert all of our energy, I didn't finish this answer, if we were to convert all of our energy, I've seen some calculations on this, everything was nuclear power, our proven reserves of uranium would be depleted in 5 years. So I don't see that necessarily as a long-term solution. Now, that's a crazy notion. We're not going to convert everything overnight, but that gives you an idea. It's a mineral that is not unlimited. There's actually a lot of uranium that's available, but it's so dispersed. So your deposits are so lean that the processing cost to get the uranium would exceed the value. Storage is kind of a challenge. And this is a kind of a real world example. If you have a haul truck, and I mentioned this morning, if you have a haul truck that has a 5,000 liter tank, that contains about 50 kilowatt hours of energy, all right? So that would give you the ability to run that truck typically on a 12-hour shift, right? At 33% efficiency, that equals about 16,500 kilowatt hours delivered to the drivetrain. Because with a combustion engine, about 67% of our energy is converted just to heat in the form of tailpipe emissions. So 16,500 kilowatts. If we were to convert that to a battery-driven system, see, batteries are much more efficient. So most of our haul trucks are diesel engine, alternator, wheel motors. And those of you in the mining industry that deal with, large haul trucks like what we deal with, for the most part, are probably configured the same way. So when you have a battery driving your wheel motors, you get much higher efficiency. You're not losing all of that energy to heat. So at 80% efficiency, you only need about 20,000 kilowatt hours energy equivalent to do the same work with that haul truck that you would utilize 50,000 kilowatt hours with diesel fuel. The problem is, if you assume a watt, that should say W-A-T-T, not W-H-A-T, I apologize for that. If you assume a watt density of 150 watt hours per kilogram, the battery's mass would be about 33 metric tons, and it would occupy 133 cubic meters of space, compared to 5 cubic meters for your diesel engine tank. So the question for you miners is, where are you going to put that 5 meter by 5 meter by 5 meter, approximately, a little over 5 meter by 5 meter by 5 meter, where are you going to put that battery? Yeah. What's that? This is not for a trip. This is, yeah. That's correct. Yeah. So what I've not included in here is also regenerative charging. So, and that brings the battery size down. But even if you get the battery down to half that size, it's still quite a bit larger than that fuel tank. So, and it still weighs quite a bit. And there are some ways, I think battery technology is going to improve. I think it's going to get more efficient. We need to be focusing on that. So I do agree with you. I do think that if you have motor-driven trucks, when they're going downhill, your motors are used as your brakes, so you get regenerative charging. So you're absolutely right. I'm trying to use simple math here, but you're absolutely right. Yeah, yeah. So that is what's going to have the charging. I haven't even covered the charging. I think if we are going to go with haul trucks to battery technology, we're going to have a modular changeout. We're not going to be able to do a serial charging, because depending upon what charging strength you want to apply to the battery, this could be a very long charge. So I think what we're going to have is a modular changeout. So the truck comes in, and rather than refilling with diesel, it basically gets a battery swapped out. Yeah, yeah. It's moving in that direction. I think I've always felt that if we want to really move in the electric vehicle area, even for our own passenger vehicles, we should be going to a modular battery service, whereby you pull into a filling station, and rather than filling up with fuel, you have a standard battery, and it's a swap out, which would make the infrastructure build out easier. Because if you've got to, even fast charging at a fast charging station, it's a long time. But I think that this is the direction we'll be going with that. Yeah.
In China, they went in that direction and sort of with the battery swap outs.
Yeah.
Got quite a big network, but that was really before the latest generation of lithium batteries. And now you're dealing with sort of about 250 watt hours per kilo.
Yeah.
Generation. And for high quality lithium batteries, you can like a 4C battery, you can charge it in 15 minutes. So the dynamics have all changed. So
It's all moving. Yeah.
I see that swap out. I can't see that happening in Australia. There was a Israeli company, what's it called, Better Place. Right, they wasted a few $1 billion of shareholder funds. They're almost as good as PhD for losing money.
Yeah.
They wasted billions of dollars of shareholder funds with that swap out model.
Yeah, so I'm not convinced on, in particular for consumer vehicles. I do actually think a swap out, a modular approach for haul trucks, just because of the sheer size and the amount of energy that we require. I think it makes sense. But I'm in agreement. Battery technology is moving very rapidly. We're moving toward much higher watt density batteries, and it'll be interesting to see how that goes in terms of we're moving towards solid state batteries as well, as opposed to liquid.
Yeah, it will be interesting to see it go, particularly with hydrogen in the mix as well, because I think that the storage technology's gotten pretty good. The pressures with the
Carbon fiber.
Technology, 700 bar and this sort of thing, and also the fuel cells are very efficient.
Yeah.
Fuel cells are extremely efficient, over 70% efficient, so very different from an internal combustion engine.
I will tell you, being the largest platinum producer in the world, I would love to see hydrogen become practical, because you need platinum group metals to make the hydrogen and to use the hydrogen. Yeah, so I would love to see that happen, and it will be interesting to see where that goes. I actually do believe that hydrogen is an extremely viable storage mechanism at a utility scale, for certain. I'm not so certain at a vehicular level, but certainly at a utility scale. I can see where when we have a surplus of renewable energy, making hydrogen and storing hydrogen is certainly something that's viable. I'm not exactly convinced at a vehicular level, but at a utility scale, absolutely see that as a possibility. And hydrogen's beautiful, because the only byproduct other than electricity, I don't think combusting hydrogen is the way to go, because you don't get the efficiency. So ammonia is a great way to transport hydrogen. I don't think transporting even cryogenically liquefied hydrogen makes a lot of sense, but for transporting it, that's already the direction that the shipping companies are moving into, is utilizing ammonia. So it's a very good carrier for the hydrogen, and much more stable as well than just pressurized pure H2, and has fewer of the effects associated with embrittlement, so on and so forth. But I really do think that as the other thing that really makes my head hurt when I start running into the math is how much renewable energy we're going to require to enable all of these different conversions, to produce hydrogen, to produce, so you can actually take hydrogen, captured carbon. I wouldn't capture it from the air, because direct air capture of carbon is extremely inefficient. We're only dealing with 420 parts per million of carbon dioxide. But you can take carbon dioxide from the air, use the Sabatier process, and then using Fischer-Tropsch, take hydrogen, carbon dioxide, and make CH4, and then you can polymerize that into whatever synthetic fuel you want. But all of those are very, very energy intensive. I do think that we can deal with renewable energies. That's not a real concern for me. The storage, to deal with the intermittency, I think is probably the biggest challenge that we'll run into.
Isn't the reliance on fresh water though?
It is a disadvantage. I will say, though, there are some interesting areas of research that are occurring, and most of that research actually is focused here in Australia. So the University of Adelaide is doing a lot of research in the area of converting salt water into hydrogen. So again, as long as we're dealing with salt water, we don't have a problem. It's fresh water that we've got an issue with. Something that's very interesting to me, and I've been in fairly regular contact with them, at the University of Melbourne, they are making hydrogen. It's still very much at the university research level, but they're making hydrogen from dissolved water in the air. So rather than requiring air in a liquid form, water in a liquid form, fresh water in a liquid form, they're taking vaporous water, so single molecules of H2O, converting that into hydrogen. So there's been a great deal of research into hydrogen that's occurring here in Australia. Those two universities are putting quite a bit of effort into it. But you're absolutely right. If you want to generate hydrogen at scale and one of those approaches doesn't work, you're going to have plenty of fresh water. And ideally, fresh water that is pure H2O. So most of our fresh water has calcium carbonate, some sodium chloride, other hardening agents, minerals. It's mineralized, they're dissolved, and they interfere with the production of hydrogen. So there's a lot. There's a lot.
With desal, you're running into brine problems and excessive amount of salt product, and what do you do with that? It's another waste product in itself too.
Yeah, so of course some of the battery technology is moving in the direction of sodium. That's something I'm not really sure. I'm not up to speed on that. But it doesn't have the same energy density. It wouldn't be utilized for mobile applications. It doesn't have the energy density that you get from lithium, but it could conceivably work at utility scale for storage. But again, there's so much research going on in this area. We just got to get it more field proven, so that we know the things that are working. And as the gentleman said, I think it's John, man, it's new every day. I mean, there's new developments every day. So whatever you're thinking is reality today could be completely changed tomorrow. Now, for those of us in industry, in mining, manufacturing, process industries, this is going to create some challenges for us. We have got to adapt to managing and maintaining these new energy systems. You know, we've got to have, sorry about that. We have to have the technical expertise to deal with them. Whether, you know, we're using wind farms and batteries and whatever the case may be, we've got to have the expertise to deal with the sustainable energy if in fact we are responsible for making and managing that energy. Integration challenges, you know, we may need to integrate different forms of energy. I will tell you at our Mahalaquina facility, it's been a real challenge figuring out how to deal with the management and maintenance of hydrogen systems, because we don't have that core expertise. So we've got to figure out, how to deal with those systems. Supply chain issues. I think we're going to probably see, for instance, if we were to completely transition to an electric society globally, it would be tough for our supply chain to keep up with everything. What did he say today in terms of how many more transformers and transmission lines, so on and so forth? That is a tremendous amount of infrastructure that has got to be made and installed by somebody. I'm not really sure how our supply chain would be able to keep up with that. And that, of course, when you have supply chain shortages, the next one's affected, cost control. Because whenever you have a supply chain shortage, the price for labor, the price for the materials, it all goes up. Regulatory compliance. I mentioned to you that the environmental world doesn't have a single agenda. It would be great if there was just one agenda in the environmental world. But in the environmental world, we have to deal with carbon dioxide, right? We have to deal with water impacts. We have to deal with impacts on flora and fauna. We have to deal with all of these various impacts that are all going to fall under regulatory compliance issues. And skill shortages. We're going to have to become better at energy management, which is one of the things that I want to get into here today. Energy variability. We're going to have to ensure that we can deal with the variability of energy. And so in South Africa, we're already dealing with this, but we're not dealing with it well. I don't know if you've heard, but we have a lot of what's called load shedding in South Africa. Our fundamental power generation and distribution system has not been looked after properly. So at any given moment, several times a day, the power just goes off. Now, they have plans for it. You can go up on an app. So when I'm in South Africa, which I leave for South Africa on Saturday, I go up in the app, Eskom, the power company, they tell you when you're going to have load shedding in your area, all right? But what happens is when we have load shedding, guess what kicks on? Diesel generators, the least environmentally responsible way to generate electricity. So, we're going to have to deal with that. Storage risks. Batteries are a problem. If we have to, incorporate a lot of battery technology into our sites. Infrastructure adaptation. Like I said, when I think about the transition to a fully electric society and the infrastructure requirements to do that, it makes my head hurt. It just makes my head hurt in terms of all of the infrastructure, transmission lines, and in particular with the intermittency in the mix, you've got battery storage. So the AC electricity that's generated by a wind turbine is going to have to be converted to DC electricity for storage in a battery and then inverted back to AC electricity. So all of that infrastructure has got to be in place. Now, solar obviously goes direct to DC, so it only has to be inverted. But if you want to store wind, you've got to convert from AC to DC, then invert DC to AC. So now that being said, you can transmit DC electricity at high voltage along long distances. In fact, we've got it's very efficient, as a matter of fact. We've got a large transmission line going in from West Texas and western Oklahoma, where the wind blows. When the wind comes sweeping down the plains, you may have heard the song Oklahoma, all the way to Memphis, Tennessee, because the way our grid system works is we have the eastern U.S. grid, we have the western U.S. grid, and we have the Texas grid. Texas got its own grid. That's Texas for you. Texas has its own grid, and your ability to cross those grid systems is very limited. Just a small amount of energy can cross. So we're building a 1,000-mile, with that 1,600-kilometer transmission line from West Texas and western Oklahoma, all the way to Memphis, which is the first entry point into the eastern grid where we have the largest population density. So lots of infrastructure requirements. Environmental impacts, change management, risk management, all of these are challenges that we have to face. Now, in industry, we consume globally, about 37% of all of the energy that is consumed on the earth. So that's about 60 billion megawatts hours per year. Existing best practice could reduce this by 12 billion megawatts. So the U.S. Department of Energy has done a number of what are called bandwidth studies. And these bandwidth studies, I've only put 3 of them up here. They've got bandwidth studies for all kinds of different industries. These are freely available. And they're based upon U.S. industry. So I think probably U.S. industry is going to be on par with the sophistication in Europe and Australia, and probably a little bit more advanced over, say, developing countries. But what they found, and I'll focus on the mining industry, is by implementing existing best practice. So we just do the things that we know that we can do, and I'm happy to share these bandwidth studies for you. They're freely available. You can just email me and I'll send them to you. We can reduce our energy consumption by 20.7%. 20.7%. And with investment in R&D, that can be reduced by 54%. I consider this part here to be what the scientists and engineers need to be working on. I don't think I'm going to be focusing on developing the newest, greatest technology for generating various forms of energy. I think this is the asset manager's challenge. If you look at all industries across the board, we have about a 20% opportunity to reduce energy consumption just by implementing existing best practices. That would have a huge impact. It would reduce our CO2 equivalent emissions. And if you look at all energy forms, all right, and you kind of do a weighted average, for every kilowatt hour of energy used, you're producing about 0.707 kilograms of carbon dioxide. This is highly variable. You know, if you use a lot of coal, it's going to be higher. If you use nuclear power, it's going to be lower. If you use hydropower, it's going to be lower. But when you look at it and kind of average it all out, according to the Department of Energy in the U.S., it's about 0.707 kilograms per kilowatt hour. That's a huge impact. Does that solve our climate issues? No. No, but it helps. I do believe that solving and confronting climate change is not going to be about doing one thing. It's going to be about doing hundreds, maybe thousands, maybe tens of thousands, maybe hundreds of thousands of different things that cumulatively and collectively move the dial. And this is something that we can do. One of the benefits to that is if you and I as asset managers do the things that are within our circle of control, if we address the things within our circle of control, we not only are doing good by the environment, reducing our CO2 impact, but that money goes straight to the bottom line. So if you save 20.4 or 20.7% of your energy, you reduce your energy consumption by 20.7%, everything that you would have spent goes directly to the bottom line. It's profit. You know, when we look at our OPEX budget, one of the big blocks in the OPEX budget is energy, whether it's electricity or buying diesel fuel or coal, if you're using coal, if you happen to be a coal-fired power plant. But that's a big part of our OPEX budget. And you take 20% off of that and you move it right to the bottom line as profit. Additionally, when you improve the energy efficiency of your systems, you are reducing the conversion of energy to destructive forms. Those destructive forms are vibration, heat, right? So you're actually improving the reliability of your equipment. You're extending the life of your equipment by managing the conversion and transfer of that energy. So it reduces wear and tear on the assets. So what can you guys do? This is the bluff. Some actions that you can take in the near term to reduce your energy consumption. I'm starting with mechanical. I'm a mechanical engineer, and then I will move into the electrical stuff that I don't understand quite as well. But number one, fasten down your equipment. So the guys from Taliesin, they attended my precision maintenance class with a focus on flab, and they learned that I'm very passionate about fastening down equipment. If you fasten down your equipment, you reduce vibration. And what do I mean by fasten down your equipment? It's nuts and bolts, right? If your equipment is allowed to move, if your equipment is loose, energy is deviating from its intended pathway. I want the energy to go to my electric motor as electricity, be efficiently converted in that induction process where electrical energy is converted into mechanical energy. I want it to be transmitted along the coupling and the shaft, and I want it to be converted into whatever work I need done, whether it's a conveyor, a pump, whatever, as efficiently as possible. If I have looseness, I'm producing vibration. So vibration, I mean, when you really look at it from a physics perspective, is converting the energy to heat. Vibration is the pathway or the mechanism by which it occurs. Likewise, with alignment and balance, if you have your equipment properly aligned and mechanically balanced, you're reducing vibration. So you're reducing energy waste. Let me show you an example here that, oh, there it is, sorry. One of my colleagues is Howard Penrose, and he's got a PhD in electrical engineering. And he's probably the foremost expert in the world on what's called electrical signature analysis, which is just a fascinating technology where you evaluate your electrical current, the signature, voltage, and amperage, and you can determine, he can find bearing defects, all kinds of different things. And he did a study on a 500 kilowatt motor and utilized 3 different alignment methods. So this was in a very controlled setting. And the motor was running under load. So he had a guy, the same artisan, align the coupling, right? Align the shafts using a straight edge. And I hate to say it, but I still see a lot of straight edge alignment at our place. So aligning with the straight edge, right? And he was able to determine that there was a 14% energy loss due to friction, 95% of which was at the drive-in bearings. Then he had that same artisan align with dial indicators, and it dropped the energy loss to 4%. Then he had that same artisan align with lasers, and the energy loss due to friction dropped to 1.5%. That's a huge differential. That's a huge, just by doing the alignment, right? The next thing is make sure that you got the right lube, that's in the right condition, that's delivered at the right time and at the right place, the right quantity, everything else. I have observed frequently in the mining industry that our electric motors are lubricated with multi-purpose grease. See it all the time. What's wrong with that? Multi-purpose grease generally has a base oil viscosity of about 220 to 320 centistokes. The ideal base oil viscosity in the grease for an electric motor is 100 centistokes. Those are the 40-degree viscosity ranges. Why is that a big deal? That extra viscosity, particularly for a higher speed motor, 1500 RPM, 3000 RPM, or for us, 18 and 3600, we're on a 60 hertz system, gets converted into heat. You're probably looking at 3 to 4% additional energy consumption just by using the wrong grease in your lubricant. So we need to make sure that we're lubricating effectively. Peter Jost, who is actually, how many have heard the word tribology? Yeah, so that's the study of surfaces in relative motion, including friction, wear, and lubrication. He's the guy who coined that term. And in the famous Jost report, he suggested that the difference between typical lubrication and excellent lubrication, really getting everything right, the right lubricant, using synthetics where it's appropriate, making sure that the lubricants are in the right quantity, they're free of contamination, is about 7.5% differential in energy. All right? So you start adding this stuff up together, the misalignment, the unbalance, the looseness producing vibration. You see the numbers just on alignment for one motor, and that was under a very, very meticulous measurement and verification process. It really does start to add up. Managing combustion efficiency, making sure in our diesel engines and other combustion systems that they're properly tuned. They're not too lean. They're not too rich. In the case of our fuel injector systems, today's engines, our diesel engines, run very high common rail pressures. And the reason for that is we want to ensure that we get effective nebulization of the fuel. What that means is we want little tiny droplets of diesel fuel in the combustion chamber because engines are adiabatically ignited. So it's pressure ignition, and the more surface area you have on the little droplets of fuel, the more efficient your combustion is. We want to make sure that our fuel is high cetane number. We want to make sure that the fuel is clean. I think in the past, the cleanliness of our diesel fuel was of less concern because our rail pressures were much lower. At these very high rail pressures, you get erosion on your injectors. And when those injectors erode, they don't nebulize as effectively. So we need to ensure that our combustion systems are managed very effectively. Leak detection and repair. We leak a ton of energy, a ton of energy. Whether it's a compressed air or compressed gas system or pressurized fluid systems, we see leaks everywhere. Anytime you're pressurizing something and it's leaking, we're losing energy. I did my first project working with ultrasonic leak detection. How many people have used ultrasonic leak detection? Okay. I had just got one of these things, so I was really itching to use it. And I was working at the time with Goodyear Tire and Rubber, and they had a capital project in the plant that I was working in. They had a capital project to buy 2 new air compressors. 2 new air compressors. They already had 10, and the 10 couldn't keep up with the demand. So we had this capital project, and I said to the boss, "Hey, Jerry, I just got this new device. It's supposed to detect leaks. The old way before ultrasound, we'd use soapy water, the soapy water test, very time-consuming." I said, give me a couple of craftspeople, tradies. Give me a couple of days. Let me see what we can come up with. He said, "Sure, go do it." And so we went out. I had the gun. Being an engineer, I wasn't allowed to use wrenches, so these guys had their tool packs with them, and I would find the leaks, and a lot of times they were able to just fix the leaks as they found them. Typically it was a fastening issue. They would just tighten something up, and if they couldn't fix it, we would put a tag on that location, and we would log the leak, and we kind of quantified, is it a big leak, small leak, kind of medium size, so that we could prioritize. After 2 days, we were able to shut off 2 compressors. So we had 10 run at full tilt. After 2 days, we were able to shut down 2. And once we got back to some of the couldn't fix as found leaks, they shut down a 3rd compressor. So they were running 10 compressors when they only needed 7. That's a tremendous amount of energy. Plus they were able to cancel that order for 2 more compressors. So they were about to add 2 more compressors. This is not uncommon. I can walk around my own sites and I see, water leaks everywhere. So leak detection and repair is a huge opportunity. We want to make sure that we are managing our electrical circuits effectively. In the FLAB class that I teach, Fasteners, Lubrication, Alignment, and Balance, Precision Maintenance, I focus a lot on mechanical stuff, but I also get into the electrical aspects of precision maintenance. And about 50% of our electrical problems are, cable to connector, connector to terminal, undersized cable. It's fastening points. It's the circuit itself. And, for instance, I'm sure all of you at one point or another have used an infrared camera to go around and look at your electrical systems. I hope you have, right? If you haven't, it's pretty cool stuff. But generally speaking, if you find a circuit that is not operating correctly, it's going to be hot. Well, that's a waste of energy. Tremendous opportunity there. All right, getting into some things that are a little bit more complex. Harmonics. We are seeing an increasing amount of what's called nonlinear loads in our facilities. So nonlinear loads are caused by lighting, because we no longer really use incandescent lights. So that's a nonlinear load. Computers are nonlinear loads. Your speed controllers in a VSD, or we call it VFD, variable frequency, variable speed drive, nonlinear loads. Most of our modern control systems are nonlinear loads, right? And when we have a lot of nonlinear loads, it produces what are called electrical harmonics. And a harmonic is a multiple of the base frequency. So here in Australia, you're on a 50 hertz frequency. So your second harmonic would be at 100 hertz, your third would be at 150, your fourth at 200, your fifth at 250, so on and so forth. The reason that these are problematic is when you have voltage at these harmonics, measurable voltage at these different harmonics, you get what's called harmonic distortion. You get harmonic distortion in your systems. That means that the sinusoid no longer looks sinusoidal. It looks irregular. And to make this very simple, when you've got harmonics in the system and your voltage is no longer sinusoidal, in order to make up for those little depressions in the summation of your sine wave, the distorted sine wave, you have to make up for that with current. And current produces heat. In fact, if you have, I've got it in my course, I don't have it up here, but if you have a 3.29% average harmonic distortion, you're going to increase your energy consumption by about 20%. So even a little tiny bit of distortion will have an impact. So we need to manage that with what are called harmonic filters. Now there's 2 types of harmonic filters. There are active harmonic filters and there are passive harmonic filters. So if you have a harmonic in your system, you can actively filter that by putting energy in the system that's 180 degrees opposite of that harmonic. Does that make sense? So if you think about your sine wave as actually a circle, right? And so if you have a harmonic here, you put an equal amount of energy over here and you offset that. That's what we call an active harmonic filter. Those are a little bit tricky because any deviations and variations in the actual harmonic may not be offset perfectly. So you may under offset or over offset, and then that energy's got to go somewhere else. Increasingly, and until Howard Penrose told me about this, if somebody would have told me this, I wouldn't have believed it. He said what we need to be doing is using passive filtration on our ground and neutral loops. And he said, I said, ground and neutral loops, you shouldn't see energy on your ground or neutral loops. He says, yeah, but you do when you have nonlinearity in your loads. And he showed me an example where the ground loop was showing, it was milliamps of energy on the ground. And he said, what impact do you think that's going to have? He said, gosh, I said, I don't think that's going to have any impact at all. Maybe a fraction of a % impact. He said, what if I told you that fixing that with a passive filter would reduce your energy consumption by 12%? I'd say, I think that you're trying to argue for perpetual motion. You're making energy. He said, yeah, that's what I thought too, until he saw it. What's happening is when you have energy on your ground and neutral, it goes back to your transformer and causes distortion in your transformer. So it's not the energy that's on the ground and neutral, it's what it does to your transformer that has the great impact. So I would encourage you, just take a multimeter out and check your amperage on your ground and neutral. Now, I was talking to some of our electrical engineers, so we have smelting operations in our platinum group metals. And I said, do you think we have any current on our ground and neutral? One of the electrical engineers said, yeah, the safety rails are hot. We've got current flowing. There's a lot of nonlinearity in a smelter because these are electrical, all single phase, a lot of problems there. So yeah, I'm seeing that. So take a look at your ground and neutrals, and if you are seeing any amperage at all, that amperage, that current is going back to your transformer, and that's where the problems occur. This guy's got a PhD in electrical engineering. It took him about 6 months to work that out. So it's fairly new information, and if you want more detail on it, just ping me. I'd be happy to get it to you. Howard's doing a lot of writing in this area, and he's had a lot of success with the use of passive harmonic filters. Another thing that he said is if you've got active harmonic filters, because you have little deviations in the voltage, the phase doesn't change, but you have deviations in what the offset should be because it changes in real time. Your actual active filters are fixed. So if you've got X number of amps here and it's deviating, but your offset is fixed, so that energy's got to go somewhere, and it makes its way to the ground and to your neutral loop. So take a look at that. Then, of course, we want to make sure that we are very, very effectively managing phase-to-phase balance. So most of our electrical systems are three-phase. So we need to ensure that we have balanced voltage, current, resistance, and inductance phase-to-phase. So generally speaking, a rule of thumb, for every 1% unbalance on voltage, you're going to see 7% current unbalance. So if you have a 3% phase-to-phase unbalance, you are going to see 21% current unbalance. And that is going to produce a lot of heat, and that basically is your energy efficiency opportunity. On inductive balance, this is something that you really want to focus on when you're having your motors rebuilt, all right, rewound. Inductive balance is the efficiency and effectiveness with which the electric motor converts electrical energy into mechanical energy, right? And you want that to be balanced across all phases. If you're out of balance, inductively out of balance, that will produce a mechanical unbalance as well. And then, of course, power factor. You want to ensure that you are properly correcting power factor. So we typically need to add, I've actually never seen where we need to add resistance. So almost always, I'll just say always, we need to add capacitance, the right amount of capacitance at the right place to ensure that we have good power factor. And then you also want to be monitoring and mitigating any kind of voltage excursions, whether you've got swell, sag, or any other power quality issues. So these are some things that we can do as maintenance, reliability, asset management professionals that will get us to that 20%. Maybe not exactly 20%. You may only get 14%, right? But that's a win. But you might get 27%, right? But when you average it out, you look at all of our industries, certainly in the mining industry, 20%, I see it there, just with the mechanical, the leakage, electrical, system management. I think 20% is very doable for us. And is this going to solve our climate problems? No. Is it going to help? Yes. Yes. And the great thing is there's no downside. It's a triple win for you. Yeah. Yeah.
Energy efficiency just wasn't something we were driven to optimize for until the last couple of years.
Yep.
And I'm probably naive to some of these opportunities. I've just been blown away by some of the wasted power, the conveyor systems, for example. Just some of the new compounds coming out for low rolling resistance, bottom covers, the decisions you make around what rollers you use, non-contact seal roller.
Absolutely. You know something, I think it wasn't on our radar screen. We were always focused, I think that we should have always had it on our value proposition, but we were always focused on driving up time or driving costs down. It just didn't show up on the radar screen. And you're right, when you really open up your eyes, there's waste everywhere. I'll give you an example, at Kumba Iron Ore, one of our operations in South Africa, I just went out with a strobe light. And if you know the diameters of your pulleys on belt-driven equipment, so our crushers, I was looking at our secondary crushers, our 8-belt systems, and if you know the diameters, you can go out with a strobe light, and let's say that you've got a 20-centimeter pulley and a 10-millimeter pulley, and you check your 10-centimeter pulley, and let's say it's turning at 1,000 RPM. Well, you know what your 20-centimeter pulley should be running, right? If this is 1,000, this should be 500. I was seeing belt slip of up to 15-16%. And you think about that, that's 15-16% energy that we're paying for. We're losing 15 to 16% of our productive throughput, and I'm just going to, don't tell my bosses, but we've burned down a few secondary crushers because you slip enough and it turns out belts will catch fire. So absolutely, it's out there. If we focus on some of these simple, I say simple, they're kind of, you've got to focus on executing them. It's a triple win for us because we reduce energy consumption and our carbon impact. We reduce our operational cost, and we improve our operational throughput. And as a bonus, generally we extend the life of the equipment by managing the energy along its intended pathway. So yeah, I see the same thing that you see. And it was kind of a wake-up call for me. Why wasn't I looking at this, for the last 25 years? I just wasn't. I wasn't showing up on the radar screen. So.
Thanks, Drew. And who would have said my old man was right, switching off the lights all the time? Drew will be available at the Prometheus Knowledge Center if you have any questions for him. Thank you again.
Yeah,
Drew,
but before you go, just real quickly, on each of these, and I knew I wouldn't have time, but you will get access to this presentation. I go into each of these in more detail for your electric motor drives, diesel engines, pumping. So I've got all kinds of detail on what you need to do. There's a lot more detail, but the presentation has more detail on what you need to do from a nuts and bolts perspective to take advantage of some of these opportunities. So as asset managers, I loved the keynote today, but we are not in a position to solve all of the sustainability problems, all the carbon problems that the world has, but we can do our piece. Yeah, absolutely. So thanks a lot, guys. Appreciate it.
There's just the tea and demo sessions out in the main area again. Thank you very much for attending.